You've been told your whole life that atoms are tiny, solid pieces of matter, like little billiard balls. But if that's true, how can something so small be mostly empty space? And how did we even find that out? The answer begins with an experiment. That wasn't supposed to change physics at all. Imagine you take a thin sheet of gold, so thin it's almost transparent. Now imagine firing tiny particles at it. Not bullets, but even smaller, alpha particles. They're fast, heavy, positively charged. So what would you expect? If atoms were solid, most of these particles should bounce back, like throwing marbles at a wall, right? But that's not what happened. Most of the particles went straight through, as if the gold foil wasn't even there. That's already strange. But then something even stranger happened. A few particles did bounce back, almost straight back. Rutherford said it was like firing a cannonball at tissue paper and having it bounce back. Pause and think. Most particles pass through. A few bounce back strongly. So what does that tell us? The atom must be mostly empty space, but inside, there must be something tiny, and extremely dense, a concentrated center. We now call it the nucleus. And here's the key idea. Those alpha particles are positively charged. The nucleus is also positively charged. And like charges repel, there's a simple rule. F equals K times Q1, Q2, divided by R squared. Don't worry about the symbols. It just says, the closer two charges get, the stronger they push each other away. So when an alpha particle comes very close to the nucleus, it feels a huge repulsive force and gets deflected, sometimes even sent backward. That's the bounce. Now we have a new model. An atom is mostly empty space, with a tiny dense nucleus at the center. Let's make it real. Imagine a football stadium. Put a grain of rice at the center. That's the nucleus. The rest? Empty space where electrons move. So when particles pass through, they usually miss the nucleus completely. But once in a while, they get too close, and the electric force pushes them away sharply. Now here's where the story takes a turn. Once we know atoms are mostly empty, we start asking new questions. What happens when something is trapped in a very small region? Let's imagine a particle in a box. If the box is large, the particle can move freely. Any energy is possible. But shrink the box, and something strange happens. The energy is no longer continuous. It becomes discrete. It comes in steps. There's a simple relation physicists use. E is proportional to 1 over L squared. This just means the smaller the box, L, the higher the energy, E. You don't need the exact formula. Just remember this. Smaller space, higher energy. This is one of the key ideas of quantum physics. When particles are confined, they can only have certain allowed energies, not anything in between, like steps on a staircase. And here's the surprising part. Change the size, and you change the energy levels, which means you change how the system behaves. Now connect this to light. Light carries energy, and there's a simple relation. E equals HF, which means energy is proportional to frequency. Higher frequency leads to higher energy, leads to bluer light. Lower frequency leads to lower energy, leads to redder light. So, if the energy levels inside a tiny system change, the color of light it emits also changes. That's the bridge, from size to energy to color. Now fast forward to today. Scientists can build tiny structures, so small, they behave like those boxes. These are quantum dots, nanometer-sized crystals. Electrons inside them are confined, and because of that, they have discrete energy levels. When an electron jumps between these levels, it emits light, and the color depends on the energy difference. So here's the magic. Bigger dot leads to lower energy, leads to red light. Smaller dot leads to higher energy, leads to blue light. Same material. Only size changes, and the color changes. Now look at your TV. Bright colors, sharp images. Where do they come from? In many modern displays, they come from quantum dots. Each tiny dot emits a precise color. Engineers control the size of these dots to control the color. Millions of these dots, working together, create the image you see. So every pixel is a direct application of quantum confinement. Now step back. Rutherford fired particles at gold just to understand atoms. He discovered the nucleus. That revealed empty space. That led us to think about how particles behave in small regions. That led to quantum confinement. And that idea is now inside your TV, from a bouncing particle to a glowing screen. But here's the deeper insight. At large scales, size doesn't matter much. But at very small scales, size controls everything. Energy, behavior, even color. And the universe is built from these tiny rules. So here's something to think about. If changing size can change color, what else in reality depends on size, in ways we don't yet see? Rutherford's accident revealed the nucleus, but more importantly, it opened the door to understanding how small things behave. And today, that understanding is everywhere, even in the screen you're looking at right now, all from a few particles that bounce the wrong way.